Hi everyone, and welcome. My name is Danny Wilcox. I'm from ARUP, and this is Tales of the Underworld. Today I want to share with you some stories and experiences from ARUP in the 12D space. I want to share how some 12D users at ARUP have been trying to improve the way we work underneath the finished surface. I'm talking about underground features like drainage, ITS, and utilities. These underground features may not always seem like the most glamorous parts of design, but project experience over the years has taught us that they are nonetheless critical to the success of multidisciplinary design projects. A key team of 12D designers at ARUP were tasked with trying to improve our engineering and modelling processes around underground features. The aim was to try and explore some recurring opportunities that were being raised in lessons learnt sessions for recent projects, and this was across the whole region. Generally, these opportunities were around how we could develop a more integrated 3D design space. Some disciplines, such as ITS, put forward a challenge to the team to investigate ways to incorporate their discipline into 12D earlier in the design process. We wanted to ensure that ITS designers were able to fully utilise 12D clash detection tools and processes to avoid late redesign on projects and even construction issues on site. High levels of iterative back and forth design between the alignment and drainage disciplines had caused budget and program issues in the past, with an opportunity to solve this within 12D. Also, increased BIM requirements to the drainage space required new processes that allowed us to change the way we assign attributes and asset data. And finally, long drawn-out processes for accurately modelling utility data, especially from potholing or dial before you dig information, were making it difficult when it came to beating the project clock. Today's presentation will be split into 3 parts with 3 different specialist presenters. I, Danny Wilcox, will be taking you through ARUP's new ITS design suite in part 1. In part 2, Darren Stewart will be focusing on some of ARUP's latest tools and processes in the drainage space. And Darren Harrison will be finishing the session in part 3, where he will run through an interesting example of where ARUP has pushed the boundaries for utility modelling on a recent project. In a day and age where BIM, federated models, and 3D design have increasingly become an expectation in the highways space, some ARUP designers have looked at how they can take it to the next level. The latest discipline to step into the 3D realm is Intelligent Transport Systems, or ITS. ITS is an application of engineering design which helps to improve safety and traffic management on various transport networks via a combination of integrated managed motorway devices and technologies. In the past, ITS engineers, designers, and drafters spent a large percentage of their time generating plans, formatting set-out tables, and coordinating with other disciplines in a 2D space. Following a set of brainstorming and research sessions between passionate coders at ARUP as well as ITS experts across the region, a plan was born to push the limits on how we could deliver intelligent transport systems designs on highways projects. The drive behind the ARUP ITS design suite was to create a one-stop shop for ITS designers to create concept designs, develop them into detailed designs, and export ready-to-print drawings. And this could all be done from within 12D model. The design suite has been critical in transitioning the ITS team's traditional 2D processes into 3D. A key benefit to this was allowing for real-time coordination of ITS infrastructure in a 3D environment. The benefits so far have extended outside the ITS discipline, with road and drainage designers able to view changes to the ITS design and react instantly within 12D. Having a collaborative 3D workspace allows us to pick up design clashes far earlier in the design process than we are used to. It means that we are working more efficiently and are providing a more coordinated design at the end of the day. The design suite was built in a way to replicate the key elements of the current ITS design workflow while removing the efficient parts of that process. It is generally broken into 4 steps: pit space proofing, conduit trench design, 3D pit creation, and export. Pits are set out in 2D using the first tab of the design suite by placing conservative space proofing blocks for a range of predefined scenarios. These blocks, once finalised, will then be used to define the layout of the ITS conduit routes in a later step. The user can select a node, generally a pit, from a predefined list based on the design authority library they have selected. They then place the pit at a coordinate and the design suite will save that data to the currently selected ITS network. Pits can be moved around in the model at later stages, and the design suite will be able to re-find their location and even link them to a road alignment control line if required. These pit blocks will form the basis of the ITS design drawings once documentation is required. The second tab of the design suite is used to create basic alignments between pit locations to start the process of creating detailed conduit routes. We wanted to ensure that the ITS design was dynamic and allowed the user to link conduit trenches to proposed pits. As ITS components are changed and moved during design development, these conduits will dynamically move with them. To create a conduit run, the user selects 2 nodes, or pits, to link between: a conduit configuration and type, and a standard depth. The design suite then generates an alignment between the pits and creates conduits based on the configuration selected. Conduit run alignments can be manually altered in the model later to create complex geometry to simulate bends and avoid other underground infrastructure as the clash detection process in 12D develops. These alignments are generated as a superalignment string type and edited in the same way as any other superalignment within 12D. Conduits within the conduit run trench are created via extrusions and then also converted to trimeshes to allow for a detailed picture of all the ITS infrastructure within a network. At this stage of the process, the design may follow a number of iterations where pits are shifted around and complex geometry is added to conduit runs to space-proof more accurately against other design disciplines. The dynamic function of the ITS design suite allows this to happen without too much pain and heartache. More importantly, this step can all happen inside 12D, rather than documenting designs from different software packages before reviewing to ensure they are aligned. Once a design starts to get closer to being locked in and is ready for more detailed clash detection, the third tab of our design suite is utilised for 3D pit creation. Standard and custom pits can be mapped to our placed nodes from step 1 and rotated to suit. Most of this is an automated process. However, the suite does allow for some manual overrides to pit types and rotations for complex situations. Our ITS team has generated a library of relevant standard pits, as well as a process for relatively easy creation of custom pit shapes. 3D pits are assigned attributes based on the original node they are used for, which allows them to form the basis of an ITS BIM model alongside the conduit trimesh. The nodes placed in step 1 don't always have to be pits. We can drop in ITS cabinets, points of supply and other components of a network as well to create the full 3D picture. This also helps with our final step of scheduling the assets. To assist in our documentation process, schedules of attributes and setout can be generated from the model. These are exported to Excel spreadsheets and added to our design drawings. This process has saved hours and hours of reviewing and re-inputting to ITS schedules as the design progresses. And it means we can apply a full-blown automated design process from concept design all the way through to documentation. I'm going to leave it there today, but hopefully that was of some interest to the audience and helps to drive innovation towards a business as usual BIM world. Get ready to ooh and ah as I now hand it over to Darren Stewart with some drainage wizardry.
Thanks for that, Danny. I can certainly endorse the ITS design suite. Anything that better shows what's really going on underneath the surface is obviously beneficial to us in the drainage space. So I'm Darren Stewart, and I'm also from ARUP. I'm hoping to give a quick rundown on some of the drainage processes and tools that ARUP has developed to better improve efficiencies and to bring a touch of consistency to how we do our day-to-day work. An ongoing goal of mine is always to minimise mundane tasks, to basically make things quicker and easier for everyone, and I hope that what I talk about today reflects that. There are obviously a multitude of challenges in 12D drainage modelling. As 12D drainage users, you really don't need me to tell you that. But what I'm going to talk about today really focuses on very much the grassroots level, or specifically how we set our workspaces up. I'm also going to give a quick demo on one or two of the tools that ARUP coders have developed for us to help us reduce those iterative back and forths that Danny mentioned earlier. So I have three key topics for you. The first is called Consistency is Key, using the power of parameter-based chains. Then I'm going to talk about beating BIM, a macro for patching uniclass codes to individual drainage elements. And finally, Does it fit? A macro to reduce multiple channel design iterations. So the first part is around consistency, or rather the lack of it. I mean, we've all been there. The first day in a new project, you're eager and raring to go. You open up the model list in 12D to get your head around things, and what do you find? A list that might as well be written in Martian. There are 1.5 million models, all named inconsistently, and none of them are making sense. So what do you do? I mean, it doesn't take a rocket scientist to work out that if model naming was consistent across your organization, those first days would be a lot simpler to deal with. We at ARUP have come to the conclusion that the best way to achieve this was to automate the process, to basically force users into a consistent approach for setting up a drainage project. So, enter parameter-based chains. ARUP drainage engineers have developed a lot of chains, ranging from plan and section exports for varying scales and visibility states, providing spatially correct pit placement, BIM outputs, automated creation of consistently named drainage models, TMR-style pit bubbles, etc., etc. But the real benefit is in how these chains use parameter value files, or PVFs. PVFs allow us to use the same set of chains for any project, with a single editable PVF for each model. We developed a PVF that has three main sections. The first is required inputs. You'll notice here that there are just 11 required inputs. Some are in relation to achieving a standardized model naming convention, and the others allow the user to specify all their output names automatically and consistently right from the outset. First up, we have the network model name. Simply, a user selected 2-digit prefix with a hard-coded backend, and allowing for optional suffixes if required. It also allows the user to set model numbers, package numbers, project WBS or BIM codes, CAD, plan, section, catchment, and pit bubble tag drawing names. And then the BIM export file numbers for IFC and 12DA formats. All these entries then feed through into each and every single chain in that list. It means the unmodified chains can be used on any project. All that's needed is to spend just a few minutes setting up 11 entries in a PVF at the very start of the project. And that's it. The next is optional inputs, which are solely for overriding corridor and cut values in the PPFs, meaning they can accommodate differently named PUP models or tri-meshes, for example, while using the exact same unmodified chains without the PPF plot outputs failing or falling over. And finally, the do not change inputs. This includes all the hard-coded parameter information that regular users really don't ever need to touch or to worry about. There are obviously far too many chains to show them all, but I'll just give a couple of quick examples. So I did mention consistent setup. Running this create new drainage models chain will set up your drainage network model, catchment models, labels, bypass and TC strings. Everything is automatically named based on the values you entered in the PVF. It means you don't ever need to edit the chains, just the PVF. And that's a huge advantage, and one that should be apparent to anyone that's ever tried to transfer a set of output chains from one major project into the next. Or this one, for adjusting drainage structures to be spatially correct. It will create and auto-name head wall and network tri-meshes, and then auto-share them out of the project. Again, these are all automatically generated from the PVF, so you know exactly what to expect because everyone's mandated to doing it the same way. So hopefully it's clear here that the main point is not about the chains. Chains have been around forever and aren't really anything new or exciting. It's all about the parameter file and how spending 2 minutes at the outset helps you keep things consistent and streamlined throughout the life of your design project. You don't necessarily need a new tool or macro or onerous process to help maintain consistency. Most of the tools are already in there from 12D. You just need to apply them in a right and consistent way. And also, just knowing that the previous 12D user in the project has set it up in the same way because he was forced to. You know you don't need to spend 2 days deciphering what models you should be using because you already know. The second part I wanted to talk to you about relates to patching attributes to a filtered drainage network. Part of the BIM requirements on a recent major infrastructure project here in Brisbane require IFC outputs to include NBS uniclass codes as attributes, and we found that using the 12D attribute manipulator only got us so far. While it's possible to create new attributes and apply them to strings within a model, they could only be applied wholesale, and then only to strings and not to individual nodes or links, or pits and pipes. Our requirements are a bit more onerous than that. We needed to apply a separate set of uniclass codes to each and every element, varying depending on the node or link type. So, an RCP needed to have a different uniclass code than, say, a PVC pipe, and a lip and line pit had a different code to a carbon line or a manhole. It appeared that out-of-the-box 12D currently didn't have the ability to achieve this. To address this, we work with Ranzu, one of our more savvy coders from our ARUP Sydney office, to create the ARUP Modify Attributes macro. In this example, the macro looks through the model and isolates all segments or pipes with a pipe type attribute of RCP wildcard. Then creates the new value in a new attribute tree, export classification uniclass product code. The macro allows the user to select between pit or pipe, then filter through the whole model for attribute type and values, before finally patching a new attribute and custom value to the filtered drainage elements. The macro allows full use of wildcards, which minimizes the number of times that it needs to be used in a chain. The same approach applies for nodes, i.e. pits. The user simply changes the target attribute type to a vertex instead of a segment and carries on as before. There's also an option to blank out or delete the current attributes by ticking or unticking this box. Once this is done, you can just simply slot this macro into a chain, as we have done in this example. The chain here basically creates a temporary duplicate network before cleaning the model of dummy nodes, no flow strings, etc. It then uses the 12D attribute manipulator to rebuild the custom attribute tree, and using the macro, applies the preset uniclass codes to each individual drainage element depending on their types. Finally, it exports IFCs and 12DAs to your preset file names, and again, all this is fully pre-populated, controlled using the PVF that you spent 2 minutes setting up at the start of the project. And this is the end result. You can see the user specified uniclass codes highlighted right there in the bottom right. This final part relates to drainage channel design, particularly that toing and froing between drainage and alignment engineers. Channel design these days appears to become a bit of a monster. Not 10 years ago, channels were simply shown as lines on a page with a note giving type, lining, dimensions, side slopes, etc., and that was accepted as the industry norm. However, modern projects generally mandate that not only do channels need to be spatially correct, they also need to be able to be fully documented, hydraulically modelled, and scheduled. There's always been several ways of modelling channels. You can use a simple Manning's calculation, quick and easy, but there's limitations, i.e. there's no modelling in 12D, so you have no idea if the channel earthworks fits or if it can even be built. You can go a step further and give the channel sizes to your alignment designer to model, but if they change anything, then you have to start reanalyzing to make sure it all still works, and plus, it can't easily be scheduled. Or you could model them as conduit links in 12D, which means you can schedule them, but then you get stuck in that same loop of toing and froing until the earthworks are finalised. So we focused our sights on trying to address this iterative process. Our goal was to provide a means that drainage designers could be confident that channel earthworks actually fit within the required extents before ever putting them in front of the alignments team. And thus, the ARUP Generate Open Channel macro was born, and this is it. First, the user selects the drainage model, interfacing tin, and an output model, and hits process. The macro then isolates channel link types and converts to fully attributed strings and points. It then uses the strings to generate channel bases based on an upstream and downstream invert level, and offsets them either side by half of the base width. Then, the macro derives the channel side slope and extrudes the sides up to the interfacing tin. In this example, we have a large channel catch drain sitting above a road. The project boundary is indicated in red. On the face of it, everything appears fine to fit fine and looks okay. When we run the macro, however, things just don't look quite so rosy. The interface lines give the channel extents and are color-coded to indicate whether the channel height is less or more than the height of the channel link as nominated in the Water Network Editor. Red strings indicate that the actual extruded height is less, and green strings indicate that the height is more. You can see in the plan here that the interface strings on the road side of the channel are red, indicating that the channel is less than the depth specified in the Water Network Editor, and so may not have the required hydraulic capacity and probably needs revisiting. You'll also notice in the cross section the interface strings on either side of the channel and visual confirmation that they extrude to the same side slope as the channel link section profile. Also, the interface string on the high side of the channel is extending outside of the project boundary for a short distance. It's pretty clear that some refinement is needed before this goes to the alignment team for their detailed modelling in tin. Using this simple graphical representation, drainage designers can easily tweak the channels and rerun the macro until they are within the allowable project extents and all showing enough height, and hopefully turn all those red lines to green. As you can see here, after adjusting the channel geometry slightly, nearly all of the capacity problems have been addressed, but it's also causing some knock-on impacts to the project boundary. You can also see clearly in the section that the cross-sectional profile height is now achieved. More refinement is probably required. However, I suspect that in this case, some thinking outside of the box might be needed. So after it's all locked down, the analysis can be rerun, schedules can easily be exported for documentation of design drawings, and the channels can finally go to the alignment modeler safe in the knowledge that they all fit within the available extents. Well, that's it from me, so thanks for listening.
Hi everyone, I'm also Darren Harrison. I'm here to discuss how we processed utility survey information we received in 2D CAD file format into usable 3D modelled information. Firstly, we're going to discuss the CAD information and what was contained in those files, what processing we applied to that, in order to project that information to the string vertices using attribution. Once we had the information there, we sent that out to a spreadsheet for further refinement, imported it, and then ran the final in-house macro and reviewed the modeled result. Then we've got a great pit macro generating tri-meshes based on a pit outline, a tin surface, and the utility service. Our pilot project located in Victoria consisted of over 1,500 utility assets. Along with that, there was roughly 55,000 text elements. This included multi-leader blocks, simple text, height labels, survey point blocks. Here we've got some examples of the survey we received in CAD file format. The black screenshots are quality B ones, within which we can see vertice labels depicting the depth of the service in reference to the final surface. Also in which it has some leader blocks. Within these leader blocks it shows the service type, depths, diameter, justification on some occasions, critical information that was used to automate the modelling of these services. On the side there, on the right, we can see some grey screenshots. These are the result of service proofing, one of which we can have a confirmation that the service was detected at a specific location, whereas the other was recorded as a non-proofing or a slab recording. This could have been because there was no service there, or there was something obstructing the detection of that service. Here is a screenshot of the exploded leader text, and also it's been moved to the origin of the actual leader. All this information is orientated to the service that it's detailing, meaning it resides in its own individual layer depending on what service it's depicting. Once here, it's perfect for importing into 12D, and then using a macro, we could do a sort of a search radius based on each vertices to look for the specific aligned text, and then import that or assign that to the string vertices using attribution. Once there, we could then send that out to a spreadsheet for further refinement using a series of lookup commands, then import that ready for our final macro, which completes the modeling process. Here you can see a screenshot of the in-house macro we created, along with the string attributes at vertice level, which is required for this macro to be functioning correctly. Using clearance options from the macro, we could fine-tune the tolerances from the utility asset element vertices and the coordinates of the text elements. This allowed us to assign the appropriate information to each vertex for later processing of information to modeled information. Okay, so once we've got all the appropriate attribution applied to the string, we now need to convert that to string properties. Firstly, we need to convert the depths to an RL. In order to do that, we tell the macro what tin surface we're referring our depths to. This will also take into account the justifications. So if there's different types of justification at each of the vertices, this macro will take care of that. Meaning if there's a top of pipe recording and the next one's a bottom of pipe, this macro will take that into account. Equally, we need to project the string properties of the diameter, or in the case of a culvert, the width and height, to the string, and in turn, once we do, it will become that appropriate shape. Also, we need to discuss how we processed potholing. So if there was a confirmed site, we would actually insert an additional horizontal vertices along the alignment. If this wasn't actually passing through that point, then the string will actually deflect to accommodate this point of the proofing being recorded. If there was a non-proofing or a slab recording, we would then use a between point. So the string won't deflect, but all the recorded slabs data would be projected to that particular point. So we could refer to it for future reference if required. Once we've got all our utilities modeled appropriately, let's discuss how we address pit creation. Firstly, to achieve the automation that we've introduced, we need an outline of the pit as a closed polygon. This can be imported from a CAD drawing, for example, or created in 12D, of course. A tin surface and a utility that will pass through the pit, although this part is optional. Firstly, we would assign a height to the top of the pit. The function would basically go through the string and find the highest point it encounters within the nominated tin and assign that to it. So it's basically a 2D string. Once we have that, now we can project the base of the tin to a nominated surface that passes through it. If there's multiple surfaces that are passing through it, the macro will adjudicate the lowest point of a surface that passed through it and project the pit accordingly to that point. But as you know, most pits finish a nominal distance past that, say 150 mils typically, which we can add to this macro and it will do it accordingly. On top of that, we can nominate a wall thickness of the pit and a base thickness as well. Then it will just sweepingly create every pit that it needs. And in turn, we'll also assign a tri-mesh name. It will create a base of pit string. The pit would also have attribution depicting the top RL, the bottom RL, the wall and base thicknesses that were entered into the function, as well as an overall depth. This in turn could be saved out to a federated model review package with the attribution there right in front of them as well. So with every change that occurred, say an alignment was adjusted, we could just simply run this function and export the result seamlessly. This is a massive game changer. Although if you don't want to use it for pit creation, I was actually using this for things like gate swings and where you just basically wanted to assign a string at a constant level to the tin. So it's not just limited, well, at least the first part of this function, just to pit creation. So here's some screenshots of the final result. This was originally to be around about 200 hours forecast for this modeling to be done manually at each string level. This was achieved, with a couple of trial and errors within 2 weeks. But the real beauty of this is now for future surveys, we have a process in place which will achieve the same within hours. Finally, a massive shout out to Ryan Zhu. He's our in-house 12D macro creating guru. Just a brilliant engineer and an even better person to work with. This will probably be the last thing that I'll be doing with ARUP before I'm moving on to another company, but upon doing so, I'll deeply miss working alongside of Ryan, who has great tolerance and a brilliant mind in creating these. So that's it, guys. I hope you enjoyed that. I hope there's something that you gained from it, and really looking forward to looking at everyone else's similar presentations. Hopefully it didn't take as long as what I did in creating this offering, and all the best, guys. Cheers.